Greetings, we are continuing with our lessons under thermodynamics, and today we will try to look at some aspects of the first law of thermodynamics. So this is what we want to try and look at today. So the first law of thermodynamics is basically an application of the law of conservation of mass. You must have made this probably in physics. Okay, the law of conservation of mass or energy. Basically, what it states is that the total energy of an isolated system remains constant, though it may change from one form to another. So the total energy of an isolated system remains constant, even if it changes from one form to another. It might only change from one form to another. So if a system is changed from a state A, assume we change a system from a state A to a state B, it undergoes a change in the internal energy from EA to EB. So we can then be able to write change in E as being equal to EB minus EA. This energy change is brought about by the evolution or absorption of heat or by work being done by the system. So it can either be done by evolution of heat or absorption evolution or absorption of heat. Okay, or we can also look at it in terms of work done, and this work is done by the system. Work done by the system. So because the total energy of the system must remain constant, this law of the first law can be expressed mathematically. We can be able to express mathematically the first law as delta E. We've already mentioned some of these things, is equal to Q minus W. And we know that Q is equal to the amount of heat supplied that is supplied to the system. W, as we all know now, W is a work done. work done by the system. So the first law can be given a basic definition of as the net energy change, the net energy change the net energy change of a closed system is equal to the heat transferred to the system minus the work done by the system, minus the work So this is how some books describe it, but you can be able to check the various textbooks, the one that I've given as a reference, to be able to understand what we are talking about there. Okay, so we can be able to then determine work done by looking at the expansion of the gas in the piston, something that I've already mentioned many times when we illustrate it. So that we have it move from here to there. So what the change we'll have there is change in volume, and the delta E is equal to Q minus W. Okay, it is equals to Q minus W. So we also know that W will be equal to P times delta V, and so we can confidently say that delta E is equal to Q minus P times delta V. So there are other definitions of the first law of thermodynamics that can also be used to describe it. Like you'll say that whenever energy of a particular type disappears, equivalent amount of another type must be produced. That whenever energy of a particular type disappears, equivalent amount of another type must be produced. That is one way that we can be able to define it. The other way is to say that the total energy of a system, its surrounding, remains constant. So it is conserved. Energy is neither created nor destroyed. That is basically what we are saying. And the third one is that it is impossible to construct a perpetual motion machine that can produce work without spending energy on it. Okay, so these formulas can be used to write an expression for finding the change in energy. An example of a question that you can try is that Find delta E, Q, and W if 2 moles of hydrogen at 3 atmospheres expand isothermally at 50 degrees Celsius and reversibly to a pressure of 1 atmospheres. So you're asked to determine delta E, Q, and W if 2 moles of hydrogen at 3 atm pressure expand isothermally at 50 degrees Celsius and reversibly to a pressure of 1 atm. So I'll just give a few solutions here. That because the operation is isothermal, and the gas is ideal, delta E will be equal to 0. Delta E will be equal to 0. So we can then have our expression where we'd say that delta E is equal to Q minus W. So if E equals to 0, then we know that Q will be equal to W. Q will be equal to W. So once we know this, then now we can be able to determine W for a reversible process. We can then determine W for a reversible process. So you can kindly calculate that and see what it gives you. Okay. You can calculate that and see what it gives you. And then, so I will want us to look at enthalpy of a system. Enthalpy of a system. So in the enthalpy of a system, we can say that in a process carried out at constant volume, like in a sealed tube, the heat content of a system is the same as internal energy. Okay? The heat content of a system is the same as the internal energy. So this is because no PV work is done, no pressure, so we are saying no PV work is done. Okay, when the process is carried out at a constant volume, delta V will be equal to 0, definitely. But in a constant pressure process, the system, which is like a gas, when you look at a constant pressure system, in a constant pressure system, in a constant pressure process, I mean, not system, but process, constant pressure process. Okay, the system expands in doing PV work. So in this case, the system expands. And there's PV work done. Okay, so the total heat content of a system at constant pressure, the total heat the total heat content, the total heat content of a system at constant pressure is equivalent to the internal energy, which we label as E plus the PV work. Okay, the PV work or the PV energy. Okay, so this is called enthalpy. This is what we are calling enthalpy. This is what we call enthalpy. It's basically derived from the word in thalpos or heat, and we represent the symbol for enthalpy is H. And so we can therefore say that H is equal to E plus PV. H is equal to E plus PV. So we want to look at H as a factor that when it depends on EP and volume, basically we are looking at it as a state function. So if we look at this equation, let us make it our equation 1. Let us look at this equation. So H depends on E, it depends on P, and it depends on V. So it depends on all these factors. So what this means is that the value of H is independent of the path by which the state of the system is changed. It does not depend on their path. It depends on these factors here. So what happens when you talk about change in enthalpy? The change in enthalpy. So if delta H, which is a change in enthalpy, is the difference of enthalpy of a system in the final state and that in the initial state, so that we see that it's the difference between H final and H initial. So delta H will be equal to H2 minus H1, or H final minus H initial. So that becomes our equation number 2. So when we substitute When we substitute the values of H2 and H1 as form of equation 1 and 2, when we relate it to equations 1 and 2, then we can say that delta H is equal to E2 plus P2 V2 in bracket minus E1 plus P1 V1. Okay, so if we collect the like terms together, then we will have E2 here minus E1 bracket plus P2 V2 minus P2 V2 minus P1 V1. Okay, and so if we look at the change in E's, where we have E2 minus E1 and then plus P2 V2 minus P1 V1, then we can say that this is delta E plus delta E plus change in PV. We can have this as delta E plus change in PV. If P is constant, if P is constant while the gas expands, if P is constant while the gas expands, then we can say that delta H is equal to delta E plus P delta V, because we are saying P is a constant. Or we can say that delta H is equal to delta E plus work plus W, which is PV work. And so that becomes our equation number 3. We know that according to first law, delta E is equal to Q minus W, where Q is the heat transferred. So this becomes our equation number 4. Equation number 4. So from these equations 3 and 4, from equations 3 and 4, this and this, then we can easily say that delta H is equal to Q when change in state occurs at constant pressure. When change in state occurs at constant pressure. So this is true when change in state occurs at constant P. Delta H is equal to Q. So delta H is equal to that. So this relationship, because it's a constant pressure, is always written as delta H is equal to Q, but with a subscript P to mean pressure. So delta H can be measured by measuring the heat of a process occurring at a constant pressure. Okay, so we can easily then be able to determine enthalpy of a reaction. And most of the time the units for delta H is kilocalories or kilojoules. The unit is most of the time kilocalories or kilojoules. Okay, so the next time we should look at the relationship between delta H and delta E. Delta H and delta E.